Vicky Wright from ICFO Barcelona, who will tell us about different quantum information techniques one can employ in foundations.
Thanks, Nuria. Yeah, so it's really great to be here. So thanks to the organizers for putting on this school again. The same as David, I was here in 2017, and I learned a lot, and also the people that I met and talked to are still people that I enjoy speaking to now. So the people around you are people you will see probably throughout your careers. So I hope this is as enjoyable as an event for you as it was for me. Okay, yeah, so in the first two lectures, I'm going to talk about semi-definite programming in quantum theory, hopefully give you a basic introduction to what that is, and then look at some sort of famous examples that exist in the theory. So you may, while studying quantum theory, have realized that positive semi-definite operators basically come up everywhere all the time. So just so we don't leave anyone behind at this point, we say an operator is positive semi-definite. So, and we will, ooh, that's not what we wanted, which we denote like this. So this is a linear operator on Hilbert space. And then we say that it's positive semi-definite if when you take this sandwich with one given vector from the Hilbert space, for any vector in the Hilbert space, this is a non-negative number. Okay, so just to clarify. Okay, and yeah, so you probably know that they appear everywhere, and the prominent examples are density operators. So those represent your states, and those are positive semi-definite. And if you do a measurement, which is represented by a POVM, the effects or the elements of this POVM also positive semi-definite. So then semi-definite programming is a tool that allows you to optimize a linear function over this set of positive semi-definite matrices, right? And I think probably the only way it can express how useful that is through Doge. Yeah, this kind of problem comes up all the time. So imagine you're in some situation where there are some parties and they're going to do some measurements, and then you were going to figure out what the best quantum state that you can use in this situation is. Then you can run an SDP to optimize over the quantum states, and that's going to help you. So the classic reference for SDPs, so semi-definite programs, SDPs, I'll say that acronym a lot, is this book by Boyd and Vandenberg. And then for some specific lecture notes, which tell you about SDPs in quantum theory, you can look at this reference. So these references are all on the final slide, and I think you all have the slides, and there are links, so you can click them. Okay, so very useful. So we start with an example. So a classic example is state discrimination. So imagine you have kind of a very weird friendship, and your friend is going to send you a quantum system. And this quantum system is going to be in one of n states. So these are these n density operators. And then once you receive this state, your job is to try and distinguish which one of the n different states the system was in. And the way you're going to do that is by performing a measurement m on the system. And this m has n outcomes, the same as the number of different states that there are. And whatever the outcome is from the measurement, that's going to be your guess for what the state was. So this task we generally call state discrimination, because you're trying to discriminate between the states. So what is the best that we can do in this situation, the highest probability of guessing correctly on average? So if the state rho x was sent to you, you're going to guess correctly if your outcome is mx, right? So the probability of getting mx given rho x was prepared is given by the Born rule here, just this trace of mx rho x. And then we'll just assume that the states are prepared with equal probability, 1 over n. So then your average probability of guessing correctly is given by this expression here. Okay, so then our problem that we were trying to solve was what is the best measurement that we can do in this situation. So I can phrase that problem how it's phrased here. So what I want to do is I want to maximize this expression, which was just this probability up here. I omitted the 1 over n because that's constant, right? So you want to maximize that such that these m's form a P over M, right? So those are just two conditions that we need, is that they sum to the identity and that they are positive semi-definite. Yeah, so, and here we're maximizing over where the mx are Hermitian d by d matrices. So this is the notation I'll use for that. Okay, so this is our problem, and this is an SDP, hooray. This is our first example. So I'll tell you generally now what an SDP is so you can see why this is an example. So this is our general form for an SDP here. And let's break it down. So at the top here, we have the objective function. So that's the thing that we're trying to maximize. And this is going to be linear. So the variable here is x. So it's linear in x because this c is like a fixed constant. And like this trace is a linear function, right? So we have the linear objective function. And then on the second line, we have a constraint. So these are linear constraints. So here each of these AIs is a Hermitian matrix and the BIs are just real numbers. So again, this is a linear expression, so these are linear constraints. So then if I leave it here, what I've got so far is an example of a linear program. So this is something that there are algorithms that will tell you the solution of. But we're actually going to add an extra constraint that our variable is also positive semi-definite. So we've got this extra semi-definite constraint. So then what we now have here is called an SDP, a semi-definite program. So that's the main thing you need to remember. It's like linear, linear, positive semi-definite, and you're golden. So a way that you can imagine what is going on is, so these are the set of these constraints here. They describe what we call the feasible set. So all the x that satisfy these two constraints live in some convex space. And then we have a linear function, which is basically just points in some direction in this space. And then we want to go as far as we can in that direction within the feasible set. And that's how the optimization works. So if I take this point, this line along here, this function will have a fixed value p. So we know we can find that value of this function within the feasible set, but we can actually go higher until the sort of optimal point. And we call this value p star, and x star is the matrix at which we find the value p star. So obviously this isn't the only kind of form that you can write an SDP in. There are other forms. So the one I've written down on the right here looks exactly the same, except for wherever we had like complex Hermitian matrices, we now have real symmetric matrices, which I'm denoting by SD. So even if you kind of constrain everything to be real, this is completely equivalent. And then you can also, instead, you can just think about the actual like entries inside the matrix. And okay, maybe I won't go into this, but now the SDP then kind of looks like this, and you just have linear constraints on these entries, and then you're saying you can kind of arrange these entries into a matrix that's positive semi-definite. Okay, and then these are all the same. So the thing you mostly need to remember is like linear, linear, and semi-definite, and then you've got an SDP. So this was our example, the state discrimination SDP. And okay, so we've got something linear at the top, and then a linear constraint here, and then a positive semi-definite. It doesn't exactly look like this. So then as an exercise for yourself, if you want to, you can try and like find the X and the C and the AIs that put it into this form. Okay, so why was I so excited when my problem was an SDP? Like, what is the motivation for the corgi? So if you find that your problem is an SDP, then you know that it's efficiently solvable. So there is some algorithm that will efficiently find this maximum for you. So this is done, I think, usually via what are called interior point methods. but I'm not going to go into what those are. But they, at worst, solve your problem in polynomial time in the size of x. So remember, x is this variable that we are maximizing over. And there may be more efficient algorithms, but what we care about is that there exists some efficient algorithm, sort of theoretically. And then a very important point about SDPs and for the theory of SDPs is that for every SDP, like there's the primal SDP is the one that I've been describing to you, and then there's a related SDP, which we call the dual SDP. And I'll try to explain what the dual is to you now. So as I was saying, every SDP has a dual SDP. So if you choose some feasible point in the set of the primal SDP and you input it into the objective function, you will get a lower bound on the optimal value, right? So you've just kind of inputted some random point from your feasible set. So you know, maybe you put some point x star and then you found p, so you know p is a lower bound. And then the cool thing about the dual SDP is that if you do the same thing, you put a feasible point into the dual SDP, as well as being an SDP in its own right, and it gives you some bound on its own value, it will give you an upper bound on this value p star. So I tried to draw like another SDP here. This diagram is slightly misleading in that these are in like different spaces, and these functions that you're maximizing or minimizing are different. So maybe it's slightly more accurate to think of a diagram like this. So p star is the optimal value of my primal SDP, and then I put in some feasible point, and maybe I try to maximize, and I'll get up to p star in this direction. And then there's a dual SDP, and this will be a minimization. And I put in some feasible point, and yeah, I can approach this d star, which is always above p star. And then the gap between these two is known as the duality gap. So then the important thing is that for some, and maybe you could say most in some sense, SDPs, this duality gap is 0, right? So actually, instead of solving the primal, you could alternatively just solve the dual, and you'll find the same value. And then if you do that, so if you solve the primal and the dual and you find that you get the same value, then this gives you a certificate for what your optimal value is, right? Because you have both a lower bound and an upper bound, and they're equal to each other. So one condition that can be satisfied to tell you that your duality gap is 0, so this is called the SDP is strongly dual. It has strong duality. So a condition for this is known as Slater's condition, which basically says that there exists a feasible point in the relative interior of the feasible set, which means that so the constraints that defined your feasible set, there's a point that strictly satisfies them. So you don't need greater than or equal to, you just need greater than. So if there's a point actually inside the set, which you can see might often be true, then you have this strong duality. Okay, so I'm going to try and explain to you how we arrive at this dual SDP. I think the first time you see this, often it kind of seems like it comes out of nowhere, so I'm going to try and motivate it. Okay, so here we have our primal SDP, and its optimal value is p star. And now what we're going to try and do is we're going to try and write down an expression which approximates this p star, but we're going to do it in a way so it always approximates it from above, so we're coming from above. But we want to write it down as an expression, right? So without any constraints here, so with none of these. But then because we don't have any constraints to help ourselves, we can introduce some new variables. And then the idea is if we introduce these new variables in a way that is SDP friendly, then we can minimize over the new variables and find a best upper bound. So this was a lot of information, but we'll go through it, and maybe this explanation will kind of fit with what I've said. So we're trying to write down expression for p star, without constraints, so in an unconstrained way. So at first, we'll just start with the objective function itself and taking the supremum. So here I'm using max to mean like maximize. So here supremum, I'm just using, instead of saying maximum, in case like there isn't a maximum, you know, in case it's like an open set and then you need to say supremum. It's not an important detail. So here's my first effort. I just take the supremum over all symmetric x of the objective function. So this is a terrible effort, right? Because this will always be unbounded, right? When I maximize, like, so this is just some fixed c, and this x can be any symmetric matrix, so I can just make this like as large as I want. So terrible effort. Because the idea being that we haven't constrained this x to being inside the feasible set. So at this point, it can be any x. So then to try and impose these constraints in a way that's included in the expression, what we're going to do is we're going to add a term which gives a punishment if x isn't in the feasible set. So this is how we're going to try and impose the constraints. So optimally, what we would do is you would just have this punishment term is like minus infinity if x is outside the feasible set and 0 if it's inside. But we want to introduce it in a SDP friendly way, which remember meant like linear and positive semi-definite. So what we do is we add this linear function of x in terms of some new variable y. And this new variable is, so this is a symmetric matrix, which is going to be positive. So then the idea is here, this is to try and impose this positivity constraint. So then if x is not positive, then I can always find a y that makes this turn negative. And that's why it's like a punishment term. So hopefully that makes sense. So if x is negative, so then it's not in the feasible set, then I get a punishment here. So then my optimum is hopefully not going to be when x is not positive. Yeah, so this is what I've written here. So if x is not positive semi-definite, then I can find a y that makes this negative. As a kind of consequence of the fact that I've tried to introduce this in a linear way, we actually get like a little reward if x is in the feasible set, right? So if x is positive semi-definite, then for any positive y, this will be like a non-negative term. So this maybe isn't something that we wanted, but it kind of just happens. So this was to try and impose the positivity constraint. To try and impose this linear equality here. So if this linear equality holds, then we have this trace of aix minus b is 0. So this is this term here. So then we can introduce a punishment for this not being 0 by just adding this multiplied by some real number, which can either be positive or negative, depending on whether this is positive or negative. So here we can always find the y's such that if this constraint isn't satisfied, then we get a punishment here. And actually, if x is in the feasible set, so if it does satisfy this, then this will be 0. So we don't have this kind of reward problem that we had before. Okay, so this is the expression that we're going to go with, the expression that we were looking for. It's known as the Lagrangian dual function. And it's a function of these extra variables that we introduced here, like the y's and the y and the yi's. And so it is approximating from above, so it's always greater than the optimal value. And the way that you can see that is that the x that maximizes this expression is included in this set, right? Because it's a symmetric matrix. So then if you put that x into this expression, you get p star here, and then you get something non-negative, and then you get something that's 0. So there's an x in here which gives you something that is greater than p star. So then when you take the supremum over all x, you're definitely going to be greater than p star. So okay, so this is always so no matter what y's you put into this function, it's always an upper bound. So now the idea is that we can minimize over these variables y, and that will give us the best upper bound. this is what this looks like. So this looks like a lot of maths, but it's actually like just 2 very simple steps, and then we'll get slightly less technical, so don't worry. So this was our problem that we were doing, okay? So we were minimizing this expression here. So then in this second step, all I've done is collected the terms that are multiplied by x. So there's the c, the y, and then the sum over yi, ai are all in here, multiplied by x. And then the only thing we have left over is the minus bi, yi's. And then the thing that you can see from this expression is that this term, because we take the supremum over x, this term is always going to be unbounded unless the thing inside the brackets is 0. Because, you know, whatever this is, then we take the supremum over x, we can just make this infinitely large. But then since we're going to take the minimum over the yi's, then there's going to be a point where this isn't unbounded, and that's going to be when this thing is equal to 0. So that's what we find, okay? So the whole thing is unbounded unless this part is equal to 0. So then we can put that into our expression. So now this is just a constraint at the bottom that this part is 0, and the only part that remained from our objective function is the sum over bi, yi. And then the final thing that we do is that we can combine these 2 constraints. So if you notice, this capital Y doesn't feature in the objective function anymore. So it's a slack variable, and we can actually remove it. So here, if Y is positive, and if you add some things to Y and you get 0, the things that you add to Y have to be negative, right? So we can express that here. So then we finally end up at the kind of final expression for our dual SDP, which, given where we started, looks surprisingly simple, right? So I know this is a lot to take in, but maybe as your first viewing of what the dual of an SDP is, maybe you now have some idea. So for our state discrimination example, this was our primal SDP, so we have all these m's as our variables, and then our dual actually looks like this. So we just have that we take the trace of some Hermitian matrix as our objective function, and then this matrix just has to be bounded below by each one of the states that we were trying to discriminate. And then something that maybe you will notice is that this dual is a lot simpler than this primal, particularly in that the size of the variable is now smaller, right? So here we had n lots of mx, and here we just have one x of the same dimension. And remember, the time that the algorithm would take was kind of based on the size of this variable. So we've kind of improved our situation. So the dual is much simpler. So then, as an exercise, if you want to understand the derivation of the dual better, you can try and do it for this SDP. And it's in a slightly different form. So I've written down for you what the Lagrangian dual function is as a kind of starting point. And like you can try and follow these steps that I went through, and hopefully you'll arrive at this SDP here. Okay, so that was what is an SDP. And now we're going to move on to using SDPs for Bell non-locality, which was excellently presented to you by Paul earlier in the week. So as a recap of what Bell non-locality is, so you're in this scenario where there are 2 parties that are spatially separated, and they each give inputs into some device and receive outputs, and they do that hopefully in a space-like separated way. And then if you have a theory which is predicting what will happen in their given implementation of this Bell scenario, then it will tell you what the probability of getting the outputs A and B is, given that they gave the inputs X and Y. And you can take these probabilities and put them into a vector, right? So then you just have a vector in a real vector space, which describes like the whole behavior of this experiment for your given setup. And then you can kind of look at the sets of vectors that you can get from different theories. So if you're looking at something in classical physics, as Paul told you, then the correlations or the behaviors that you can see will be contained in this polytope that we call the local polytope. And then something that Paul explained to you was that you can write this local polytope so it's all the points that are a convex combination of the deterministic strategies that Alice and Bob can do. So a deterministic strategy is like, Alice is like, whenever my input is 0, I will always output 0. Whenever my input is 1, maybe I still always output 0. And then Bob has some rule as well. So the probabilities that come in this vector will all be 0s and 1s, okay? And then with all the combinations of those strategies, you'll get to some number of vertices. And then if you can write your behavior as a convex combination of those, then you know it's in the local polytope. So then we can try and express like a program that tells us if I give you a behavior P, is it inside the local polytope? So is P in L? And this is going to look like what I've written here. So if we're just trying to see if a point is in a feasible set, what we often do is we write maximize, but we write 0 here instead of maximizing some function. And then what the output of the program will be is either like feasible or infeasible, which tells you, yes, it's in the set or it's not in the set. And the thing that we're going to maximize over is these coefficients, Cj, which were like what we multiply the deterministic vertices by to try and find the decomposition in terms of the deterministic points. So what we're trying to do is we're trying to find these Cjs such that our behavior P is equal to the sum over Cj dj, where these are the deterministic behaviors. So we're looking to see if these Cjs exist. And then the things that we want them to satisfy, so we want this to be a convex combination, which means that they sum to 1 and each of them are positive. So this is a way to write as a linear program to determine whether P is in the set L. And you can see this is a linear program because these are linear constraints, right? So this C is just a real number, right? So this isn't a matrix, so this isn't a positive semi-definite constraint. This is just a linear inequality. So this is a linear program. And then you can actually look at the dual of this program, which is, so I was just telling you about the duals. So linear programs have duals the same way that SDPs have duals. And you get something that's actually kind of helpful. So basically, if you input a non-local behavior, the output will be a Bell inequality that is violated by that non-local behavior. So this is a pretty helpful thing to be able to access. And okay, so you all know, you're experts in finding the dual now, so you can do this for yourself. And what you find, so this constraint here is saying that you have this vector, and when you take the inner product with any of your deterministic vertices, it's less than some number S. So this is a Bell inequality, like Paul was explaining to you. So then when you find this B, that is the thing that gives you your Bell inequality, and then this S is the local bound. So when you run this program, you will find the B and the S, so then you know what the Bell inequality is. Okay, so now we will think about the quantum case. What time do I finish, Nuria?
So we'll make a break at 11.
At 11, okay, cool. So we're in our Bell scenario again. But now we're imagining that we have a shared quantum system, which is in some state rho, and Alice and Bob can perform some POVMs on their half of the shared system. Yeah, and again, we can take our behavior, which will just be one of these vectors, and now it will be in the set Q, which is a superset of L, superset of the local polytope. And the way that we can characterize it is if we have some quantum realization. So mx is Alice's POVM, given that she inputs x, and ny is Bob's POVM, given that he inputs y. And yeah, so I'm hoping that you remember this from Paul's lectures. So now we can ask ourselves the same question for the quantum set as we did for the local set. Is P in Q? And if I write this as sort of an algorithm, this is going to look like this. So we're using this maximize zero trick where we're just trying to see if there exists something in the feasible set again. And yeah, so we have the condition that your behavior is equal to the trace of mxa tensor nyb rho. So this is the quantum realization, and then we want to impose that this is a POVM, this is a POVM, and this is a density operator. So they're all positive, positive semi-definite, and the m's and the n's sum to the identity, and the density operator rho has trace 1. Okay, so if you can solve this, then you would know that the behavior is in the quantum set. So now the question for you is this an SDP? I'm not actually going to make you answer, don't worry. So let's look. So at the bottom, what have we got? We got some linear constraints, right? Trace rho, that's linear, equals to 1, fine. These operators sum to the identity, also linear, that's fine. These operators are positive semi-definite, all right? So we're chill with this, right? Like, these are things that we've seen before in the previous slides. Everything's good, nice constraints. Now we go to here. This is non-linear, right? Because so all of these, the m's, the n's, and the rhos are our variables, and now we're multiplying them together. Okay, so this is non-linear. So we might have to use something a bit more fancy if we want to deal with this. But then we kind of look up here, and actually we realize that our dimension is unbounded, right? So we're not in some fixed dimension looking at Hermitian D by D matrices. This dimension is unbounded. So we're going to have to get like super fancy if we want to deal with this problem. And actually, this problem is undecidable. So there is no algorithm where if I give you a generic behavior P, it will tell you whether there is a quantum realization for that P. So that's very sad, right? Like, that's a total nightmare. What are we going to do? And the obvious answer is relax, like this frog. But I mean, something slightly more technical in that we're going to relax the problem. So instead of asking whether the P is in Q, we're going to ask if P is in some slightly larger set than Q. So this is like a relaxation of the problem. We're relaxing our constraints to something slightly more, slightly less restricted. So a couple of points before we do the relaxation, which is going to make our lives easier. So if you have some quantum realization for your behavior P in terms of POVMs and density operators, then there is also a realization in terms of projective measurements. So now each of these P's and Q's square to themselves, they're projections, and pure states. So we just take this inner product, take this like expectation value for pure states. So okay, to do this, you maybe have to go to a larger Hilbert space, but remember we were optimizing over like any Hilbert space, so this isn't important. So this will make our lives a little bit simpler. And then the second point, which you can kind of view as our first relaxation of the problem if you want, is that if there exists, so here you have two Hilbert spaces which we've tensored together, and then the pure state lives on the tensor product of those. So if this exists, then there also exists, you can just think of one big Hilbert space, and these P's and Q's act on the full Hilbert space, but they commute with each other. So this is like a slight, so in this formulation, this P would be like P tensor the identity in the other formulation. So you can see that the left-hand side, is that the left? Yes. The left-hand side implies the right-hand side. And this set is known, I guess, by various names, but I'm going to call it the commuting quantum correlations because of this commutation relation, QC. And this was an open question for a long time, whether the implication also goes the other way. And it was known as Cyrilson's problem, and it was resolved, I believe, in 2020 in this paper, which is helpfully called MIP star equals RE, which tells you a lot. Yes, so we have the implication doesn't go the other way, so then in some sense this is a relaxation of our problem, right? So if we find that we can describe P like this is going to be a strictly larger set that we're deciding whether P is in than the original Q. And this is the problem that we're going to consider from now on, whether P is in this QC. Okay, and so how are we going to do that, given what we've found so far? So if it's a relaxation, then what we need to find is that if there is a quantum realization, then it implies some other condition, and then we search for whether that other condition is satisfied. So this is like a necessary condition, but not sufficient. And the way that we will do this is, so given that these objects exist, we can build what is called a gram matrix from the vectors that I've written here. So this is the state vector, and then this is the state vector with each P acting on it. Remember, the P now acts on the full Hilbert space. And this is the vector with each one of the Q's acting on it. And maybe you're like, what's a gram matrix? Don't worry, got you. So if you have some set of vectors, which we call V1, V2, V3, then you can build a gram matrix for them by just taking the inner products of all the different pairs that are in the vector. So the element ij, this gamma is going to be the gram matrix. So the element ij is just the inner product of the vector vi with the vector vj. So then the whole thing looks like this. And the good thing about this is that it's positive semi-definite. So that should be giving you some good vibes, given what we were saying earlier. Okay. So we build this gram matrix. So we can label the each element of this matrix by like what operator is in front of our state, okay? So then I've labeled the columns, the rows and the columns by these operators. And our matrix, which took me a long time, so please appreciate that. I filled in all of these things. Is going to look like this. So notation-wise, what's happened here is, so remember this is what so if we were looking at like this pxa, the element where we're taking the inner product of pxa psi with qyb psi, then because p is self-adjoint, you can just move it over to the other side. Very helpful. And then this element will just look like the expectation value of this PQ. So then I've omitted all of the psi's in this vector. So this, hopefully you can see, this is what these are supposed to stand for. So we can build this gram matrix, and what we're going to look at is what properties this matrix will have, and then that's going to be the problem that we solve. Like, we look for a matrix with those properties. So to start with, got this top left element. This is this has just got the identity in the middle, right? So this is going to be 1. It's just the inner product of our state with itself, which is 1 because our state is normalized. So we can assume that this top left element is 1. Okay, and then each of these elements, so for example, the expectation of P00, this is just the marginal probability that Alice will see on her side. And you can see why that is from this calculation. So this is what I'm denoting by this. And then you can write this, so for any one of the QY measurements, if you sum it over B, you'll get the identity. So we kind of just stick in the identity in here. And then this is just one of the elements of our behavior, right? It's the element where Alice inputs 0 and gets the output 0, and Bob inputs Y and gets the output B. So these is these elements of the behavior summed over B. So then this is something that you can calculate from your input vector, right? So you're getting this input vector, and so then you can find each of these terms from the vector, and they're given by these. So these are all fixed, and now we have some more constraints. So each one of these is exactly one element from your behavior vector, right? So this one is just the 0, 0, 0, 0. So you can replace those by the elements from the vector that they are. And then, so these are two different outcomes of one measurement on the same, of the same party. So then they are orthogonal to each other, right? So they are orthogonal projections. So these are going to be 0. And we know that the whole matrix is Hermitian, so everything that's in the lower triangle is just equal to everything in the upper triangle, so then these are all fixed as well. So then the only unfixed elements that you can see in this part of the matrix are these. There'll also be some like Q ones. So these are the ones that we can't fix given the behavior. And we call this whole matrix gamma, and it's known as a moment matrix. So what is our SDP trying to do? So it's trying to see if there exists, so we know that this matrix has to be positive semi-definite, and we know that some elements of it have to be given by some linear combinations of the elements from our behavior vector. So this is a necessary condition for P to be in the set Q, right? So if P is in Q, then we can construct a vector which has these properties. So then this is a relaxation of P being in the set Q. And just maybe a slightly subtle point is that we can actually restrict this to being symmetric instead of Hermitian, so all the terms being real, because, where did it go? Yeah, it's there. Clearly, if there's a symmetric matrix, then there is a Hermitian matrix, because a symmetric matrix is Hermitian. And then for the implication in the other direction, if you have a Hermitian matrix with these properties, then if you add it to its own complex conjugate and divide by 2, then it also satisfies these properties as well. So we don't have to maximize over Hermitian, now we can just restrict to symmetric, so everything stays real. So this is something that we can write as an SDP. So we're maximizing over the symmetric matrix, and we're using this trick where we just have 0 because we're seeing if it's feasible. And some elements of our matrix have to be equal to some linear combinations of elements from the input vector P, and it has to be positive semi-definite. Pretty simple. And so if this is true, if this problem is feasible, then we say that the point is in the set Q1. So this is a relaxation of our set Q. And we'll get on to what Q2 is slightly later. Okay, maybe actually I think it's time, so I'll stop there. And then we'll have the break, right? Okay, thanks. Okay, oh yeah, I'm working. Cool, okay. So what we looked at so far is we have an SDP that tells you whether your behavior is in a set which we're calling Q1, which is a superset of the set Q of quantum correlations. And soon we'll go on to the fact that there are sort of there's a hierarchy of these sets which approach Q. But first, we'll just look at the very closely related problem of maximizing a Bell functional over the set Q1. Okay, because this is something that we can also do. Instead of just asking whether our behavior is in Q1, we can try and find like the maximal violation of some Bell inequality within this slightly expanded set of correlations. So a quick recap of what a Bell functional is. So we're in this real vector space where our behaviors P live, and then we just have some linear functional which you can express by just taking the inner product with your vector of behaviors, and we call this W a Bell functional. So on this diagram, it looks like very similar to in our SDP case. So this functional will increase linearly in some direction, and then on the local set, we'll be able to find like some maximum value of it. So in this case, it would be if you take some behavior somewhere along this line, the value that you get here. So this so if we take W dotted with P, if P is in the local set, it'll always be less than or equal to some SL. So so this will be the points on this line which give you this value. Oh, I didn't do the quantum one. Boo. And then you can evaluate the same functional over the quantum set, and then sometimes you can find a greater value in the quantum set. So this is what the Bell functional is. Okay, so we're going to think about the CHSH scenario, which is you have these two parties and they each have two inputs and two outputs. It was what Paul called the workhorse of the Bell non-locality world. So then our matrix, in the way that I explained it to you before, would be indexed by all of these things, right? So we have the zero measurement, the one measurement, the zero measurement, the one measurement on both sides, and two outcomes. But something that we can see, which is always true, is that the column that comes from the second outcome, for example, of Alice's first measurement. So this operator is just given by the identity minus the operator for the first outcome, the zero outcome. So then everything in this column is just given by what's in this column minus what's in this column. So they're just like completely linearly dependent on each other, so then they don't help us in any way or give us any extra constraints. So we can remove all of these. And that's going to make our life a lot easier, because now we just have a 5x5 matrix to deal with. And then the second kind of neat trick that we can do, so that trick is true for like any number of inputs, outputs, parties, right? You never have to consider the final outcome. But when we're in this case where we have two outputs, what you're seeing here is that you have one operator for every single measurement, right? So you just have the operator for like the zero outcome of each of the four measurements. So instead, we can replace this by the observable. Instead of looking at the projection for the first outcome, we can just look at the operator, which is the observable for the whole measurement. So then if we label, slightly confusingly, if we label the first outcome of the measurement with a 1 and the second outcome with a -1, then your observable is going to look like this. So you just take one minus the other one. So, for example, wait, maybe I can write this. So this would be like sigma x if your projections were like 1/2 the identity plus sigma x. And a half the identity minus sigma x, then this is just like the observable for that measurement, which is sigma x. Okay, I can remove that. Oh, very slowly. Oh, okay. So now, if we use these operators instead to build our gram matrix, and the reason that we will do this is because we're going to look at the CHSH inequality. And you can very neatly express this in terms of these expectation values on the observables instead of using the projections. And it's just going to make everything a little bit simpler. Okay, so instead of looking at a matrix indexed by these things, we look at one indexed by the observables instead. And again, I filled all these in for you because I'm very generous. So this is everything we've got. And remember, these are like expectation values. And so because of the way that we set up this A0, it was just like a plus times by a projection and a minus times by a projection. So if you square that, the projections, wait, this doesn't make sense, but they square to the identity, basically, is what I'm trying to tell you. So then all of the elements along the diagonal will be 1. And now, then, again, if you look at the CHSH inequality, each of these objects are given by just some elements of this matrix, right? These 4 elements here. So then we can write our SDP in like this very neat, small form. So it's basically just you sum and then minus these elements of this matrix, and all the matrix has to satisfy is that these diagonals are 1 and that it's positive semi-definite, and that's like everything from our restrictions that we imposed before. Like this is equivalent to the level 1. So I wrote this for you in like the simplest way possible, and I apologize for my bad coding. But I'm just writing this so that you can, if you've never written an SDP before, you can like look at this and try and see what all the things do, like look at the slides afterwards. And what you'll see, so this part down here is like the output of the SDP. So it tells you what this moment matrix was, which maximized the program, and it comes out to be something that looks like this. And then it gives you what the maximal value of the Bell inequality is, and this is the 2√2, which we wanted to reproduce. So in the case of CHSH, level 1 is like tight. So you actually get the 2√2 that you can get in quantum. So like the boundaries of the Q1 and Q like touching. So to do this, if you've never done something like this before, the setup that's being used here is I used MATLAB, and then you have to download YALMIP and then some solver. So my solver here was Mosaic. So you can find kind of guides for how to do this, like on the websites for these things. And hopefully you can set this up for yourself. There are obviously other ways to run your SDPs if you want to. But if you don't have a way so far and you have a MATLAB license, you can use this. If you don't, you can also use Octave, which is like the kind of free version of MATLAB, and YALMIP and Mosaic work with that fine. So then, if you're doing this for yourself and you want like a kind of simple challenge to expand what I've written for you here, you can try to find the maximum value in Q1 for what's called the tilted CHSH inequality. So this was our CHSH functional, and then you just add this extra term here for some alpha between 0 and 2. So this is something to have a go at. Okay, so now to the levels. So what I described to you first is what we call level 1, and we're building the gram matrix from these vectors. So there's some operator which comes from the set of the identity, the P's and the Q's, multiplied by the state vector. So then we can go to level 2, and that we basically just have 2 operators from this set in front of our state now instead, and then you build your moment matrix in the same way, and then look for all the constraints that you can impose on these. And then you can go on like A, B, C, and however many operators you want in front of the state vector. And this is called the NPA hierarchy. So they have multiple papers on this. So I just gave you one as a reference, but you can find the other ones from this one. And the extra cool thing about the NPA hierarchy is that if you take the limit in the levels, you will actually converge to the quantum set itself. So in theory, eventually, you can always find this maximum value, but be aware that this program will get like really, really big really quickly, so it's hard to run higher levels. So obviously, it'd be nice to code this yourself, but if you don't quite feel like it, you can use, I've given you a reference to something that was an implementation written by Peter Vitek, and you can hopefully figure it out from there. Okay, so this kind of seemed to, oh, hello.
I have a question about the undecidability you mentioned before.
Oh, yes.
How does that relate to the convergence?
So then, so you will never find out. So because you need to go to infinite levels, if P is in the set, you will never get the answer yes, right? So you will always get maybe, 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 maybe forever. So then you don't have a program that's deciding this, right? So if it's outside, eventually you'll get the answer no. But if it's inside, you'll never get the answer, right? So that's how it relates to the undecidability. Yeah, I should have said that, so thank you. Yeah, okay, so maybe you saw this moment matrix being built and you were just like, why? Why are we doing this? It doesn't make any sense. This little dude always has this. Okay, so I think a good explanation of this you can find in this reference here. And how long do I have? So this would finish at 12, right? Okay, so I'll just try and give you a brief flavor of this argument. So the idea comes from a problem of polynomial optimization in a way that Lasserre tried to solve it. So for polynomial optimization, so we have some polynomial in our two variables, x and y, which are real. And then we have some polynomial constraints. So, you know, x squared minus x is equal to 0, and they have this inequalities for the y. So this is not an SDP, right? Because everything is nonlinear all over the place. So then what Lasserre's idea was is that you can introduce some variables which are given by a basis of monomials. So a polynomial, you have like some sum of terms which are like your variables multiplied together. And a monomial is if you just have like one of those. So like xy is a monomial. So if you think of these as your variables, then this is linear now, right? So xy, we call this variable like m12. So now just in this variable, xy is now just a linear thing, right? So this is the idea. You have some basis of the monomials. So now all your polynomial things are now linear. But for this optimization to like actually find the right thing, you need to impose that there are some relationships between your new variables, right? So for example, the variables m1 and m2, which are x and y, is equal to the variable m12, which is xy. So then his idea was that you can impose a kind of relaxation of this relationship by saying that this matrix which you build from your variables has to be positive semi-definite. And it kind of works in the same way as the moment matrix that we were looking at before. So in this matrix, what we've done is, so in the M1 sort of position, instead of putting, what would that be? Now I got confused. Oh yeah, instead of putting like M1 squared, we know that M1 squared is M1 because of this constraint here, that x squared is equal to x. So you're kind of building these relationships into this matrix. And then if you multiply this by on either side by some vector and then look at it element-wise, you can convince yourself that this will always be positive semi-definite. And this is like a relaxation of the relationships between these. And then you can make this basis bigger and bigger in the same way that we could make our moment matrix bigger and bigger to better approximate the problem. And yeah, and then you also impose the inequality constraints similarly by some matrix. So this was very fast, but if you look in this paper, there's like a nice example and it starts to kind of make sense and it gives you some motivation. And the relationship with what we were looking at is that our Bell operator is basically is a polynomial in these, the A1s and the B1s, but now it's a non-commutative polynomial. So here everything commutes with each other, like xy is equal to yx, but here it doesn't. So you have to kind of expand slightly. So then the problems that we're looking at are known as non-commutative polynomial optimization. So this is something that you can look into if you want to understand better. Okay, so now I just have a list of cool things about MPA. So obviously the first cool thing is we had this problem that we couldn't really solve, and now we can kind of get some good bounds on the answer to it, right? Which I didn't include in the list, and I probably should have. But the first thing that I've written is that it gives you, in general, an approach to dealing with like quantum problems where the dimension isn't bounded. So we can use it in other situations as well, and soon, next, I'll move on to contextuality, and you can see that we use a similar approach there. The second thing is that if you look at the joule of the SDP that I just told you for MPA, this will give you what is known as the sum of squares decomposition of the Bell operator. So I just will briefly explain to you what sum of squares is and why it's useful. So this was our CHSH operator here, and then the thing that we're trying to maximize is this whole expression, right, where we can put in any observables A and B into this expression, and any states. So we call this whole thing the Bell operator W, and then what we're looking for is, so if you take the inner product of W with some state, we're looking for like the biggest value that you can get there. That's the same problem that we were trying to solve before. But one way, something you can see is that this will actually just be the largest eigenvalue of this operator, right? So if you look at like the spectral decomposition of W, then you take the operator which has the largest eigenvalue, then take the inner product with that, you'll get lambda, and this is the best that you can do. So I can rewrite this expression by just putting the identity with the lambda here and taking this inner product. So then you can see that the equivalent condition is that if I have lambda I minus W, this is a positive operator. So this is like another way of writing the same problem, is trying to show for which lambdas is this operator positive. So this holds, and so this will be positive for any lambda greater than the largest eigenvalue. So then you're trying to find the smallest lambda that it's so that it's positive. Yeah, and this is giving you an upper bound on the max value. So then now your problem has been converted to showing that this thing is a positive operator. And how can you show that? And one way to show that an operator is positive is to show that it has a sum of squares decomposition. So basically you can write it as like this. So if it's a sum of squares, then it's always positive. So what the joule of the NPA, say at level Q1, gives you is that you'll be able to get out of that program what these operators P are in the sum of squares decomposition, where lambda is the optimal value that you find at level Q1. And this is nice because it then gives you like an analytical way of showing that this lambda is an upper bound on the maximum quantum value. So you're not just relying on this program anymore. If you have the sum of squares, then you now have like a kind of certificate for this, but like an analytical one. Okay, and so the third thing on my list is that if you look at level 1 plus AB, so this is between levels 1 and 2, we have like a different characterization of this in terms of Hilbert space, and these are called the set of almost quantum correlations, and they're quite close to the set of quantum correlations. So then if you're interested in this question that Paul was asking of like, what are some physical requirements that you can place on like the world that would get out the set of quantum correlations, the almost quantum correlations are like a very good test case for this, because like distinguishing between almost quantum and quantum is like pretty hard. So and they're useful in many ways. And the final thing is, so it's suggested that it might be possible to solve what is known as the MUB problem. So the problem of finding out how many mutually unbiased bases there are in a given dimension. You may have heard of this, you may have not. You can Google it if you want to. But this is kind of a foundational problem or a maths problem in quantum theory that has been open for a long time. And there's the idea that if you apply the MPA in the right way, you can actually find out the answer to this. But at the minute, it gets like too big too quickly, so people haven't been able to implement this. But I know that there are people still trying in different ways, so this could, in theory, happen eventually. Oops, we'll go through this again. Okay, so now, as promised, we'll move on to contextuality. I had a really bad picture of David, and then he gave me this picture, which also seems quite bad, until you look at the next picture, where it's really good. So yeah, this is to show you how exciting contextuality is. Okay, so quick recap. What is a contextuality scenario? So David has told you a lot about this, but we're just going to consider a prepare and measure scenario. So you have an input X, which tells you what preparation to make for your system. Then you have an input Y, which tells you what measurement to make, and then you'll get some output K from that measurement. And then, so from that, you get this vector, the same as we did in the Bell scenario of the probability of K given X, Y. And now, instead of just the number of inputs and outputs to specify a scenario, which I'm calling X, Y, K here, we also have some operational equivalences on the preparations and on the measurements. So an example would be that, so if you had 6 preparations, maybe if you took an equal mixture of the first 2, this is operationally equivalent to an equal mixture of the second 2, and the same again for the unequal mixture of the third 2. So I'm hoping you remember what operational equivalence is, but it basically means if you did any measurement on one of these mixtures, the statistics wouldn't be able to distinguish between the other mixture, right? So you can't distinguish them. And similarly, so this was OEP, and you also have OEM, operational equivalences on the measurements. So here I have 3 measurements with 2 outcomes each. And if I take an equal mixture of the first outcomes of each of these measurements, I'm saying it's operationally equivalent to an equal mixture of the second outcome of all 3 of the measurements. So David talked a lot about this, so I'm hoping that you know this. So an example for these 2 operational equivalences of some states and measurements in quantum theory that would satisfy them. So if this is a plane of the block ball, then our states here, we got row 0 and row 1, and they equally mix to the maximally mixed state identity over 2. And then the same for like 2 and 3, because they're opposite, and 4 and 5. And then similarly, these are some projections that would be like the 0 outcomes of the first measurement, and they mix to the identity, and the same for the 1 outcomes. So this is like a quantum implementation. So we can compare our contextuality scenarios with the Bell scenario. So this is the picture that we were looking at for the Bell scenario. We have these 3 sets, and then we get, in my drawing, an almost identical picture for the non-contextuality, for the contextuality case. So here, the inner polytope is if your model is non-contextual, then the behaviors that you can get out in this scenario lay within this polytope, NC, which is non-contextual. And then we got Q for if you're doing a quantum thing, and then you can go even more general for just some general GPT to get some behavior C outside of this. And the same way that you have Bell inequalities, you can have contextuality inequalities, which are just like a linear. You just take a inner product with some fixed vector on your P vector, and there'll be a largest value that you can get for this. So then to define the non-contextual set, so an example in our case with these preparation equivalences and measurement equivalences, of a contextuality inequality is you just sum these three elements of the behavior vector, and you will find that this will always be less than 2.5. And in order to determine whether your behavior is inside the set NC, in the same way with the local set of correlations, this is a linear program, and you can find it at this reference. It's a little bit more complicated maybe to realize what the vertices are, because before it was just these deterministic points, but if you read this, you can understand. But we're going to be more concerned with the quantum case, so I will focus on that. So now we're trying to figure out whether our behavior P is in set Q again. So that would mean that there exists some density operators, rho x, one for each preparation, and some POVMs, E, Y, such that you can get these probabilities from the Born rule with these states and measurements. But then also the extra requirement is that they have to satisfy the preparation equivalences, which in quantum theory, they come out looking very nice, like the same basically as they look in the operational form. And then just as an example for the contextuality inequality we considered before, the quantum value that you can get is around this. And the way that we found this was using an SDP hierarchy similar to the NPA one that we talked about, and that's what I'm going to explain to you now. So before I do, there's a couple of differences with the non-locality case that we need to think about first. And that is that, so before we had that we could restrict, so in non-locality we could restrict to pure states and projective measurements. So what if we do that in this case? So now if in this definition I remove where it was density operator and I put that this is a pure state, and it has to be a pure state here, and the pure state would satisfy these equivalences still. So what you find now is that in general this will give you a subset of the quantum behaviors. And it's drawn as a heart here because we didn't even manage to show that this would be convex. So this is kind of a weird set. So if you feel like doing that, like, have a go. And we've called it Q psi. So this is a subset, so we know that we can't restrict to pure states. And then similarly, if we replace POVM with PVM, so like a projective measurement, you also get a strict subset of Q in general, so we can't restrict to projective measurements. So this is what this diagram is supposed to represent, like we can't restrict to pure or projective. Okay, so we're going to try and do the same process that we did before with our gram matrix, but things that will be a little bit different because of this problem that I just described. So now, okay, so if this P is in our set, then there exists these operators E and rho, such that you get the vector from the Born rule. So then if they exist, then we can build a gram matrix from them again. And our gram matrix is going to look like this. It may not be immediately obvious why that this is an inner product of like some pairs from a set of vectors. But if you consider the set of vectors, so now the vector space is the like Hermitian operators or self-adjoint operators on a Hilbert space. So this is a real vector space. And then if you now consider for some operator Oj that we put in front of our density operator, but to the power of a half. So a positive operator will always have a unique positive square root, and that's what this is. And on this vector space, our inner product, A inner product B, is going to be the Hilbert-Schmidt inner product. So we take the trace of A dagger with B. So that's why we end up with this dagger here. Yeah, so now our gram matrix is given in the standard way, but using this inner product instead. And you end up with this form, which is the form that I'm showing you here. So this is what our moment matrix is now going to look like. So we can, so for this set of operators Oj here, I've chosen the POVM elements from our realization. and I was slightly more lazy this time, I'm sorry, and I didn't fill in all the elements. Please forgive me. So just using this formula, this is what the elements will look like. And a simplification we can make is we get 1 here in the top corner, and then along the first row and column, these are simply given by the elements of our behavior. So these will just be given by the P's. So here I'm choosing the O's as the effects. So now we can write down what our relaxation is of the, trying to find the quantum set of contextual behaviors. So it will be, so we're looking for that there exists. So now for every state there is a moment matrix. So our moment matrix is indexed by this X. So we're looking for these moment matrices, gamma X, and they will be positive. And then they will satisfy the operational equivalences. So for the preparation equivalences, it actually turns out you can just write it for the whole matrix itself, and that's what the constraints start to look like. For the measurement equivalences, it's a little bit more fiddly, and you have to go element by element, but it's just a linear constraint on the moment matrix. And then finally, as I was saying, the first row and the first column are just given by elements of your behavior P. So now we're solving a similar problem where we're just looking for the existence of these positive matrices. But as I've told you in its current formulation, this is terrible. So along this diagonal, before, when we could restrict to projective measurements in the non-locality case, when you would square this operator here, you would just get the operator itself back because it's a projection. So then you could write that these diagonal elements were equal to elements from your behavior. But now we haven't got that constraint. And actually, when you try and do the maximization, you will find that you can make these as big as you want, which means that you can basically, it won't give you anything good in the end. It won't discern between behaviors that are inside or outside of any set. It's just unbounded. So this is rubbish as it is because of this projective measurement problem. So then, unbounded. So problem, cannot assume projective measurements. So what was our solution to this problem? So there is a helpful lemma that we can use, which tells us that for any effect, we can find a unitary matrix U such that E is equal to the identity over 2 plus U plus U dagger over 4. So this is just a fact about POVM elements. So now what we do is instead of indexing our moment matrix by the POVM elements, we index it by these unitary operators U, which are linearly related to the POVM elements, so everything will work out fine. So for example, when we had the constraint that before the first row and column had to be equal to exactly the elements from the behavior, now we just get that they are some linear map on the elements from the behavior. So all of our constraints are staying linear. But the good thing now is that along the diagonal, sorry, that was a surprise for later. Along the diagonal, so we're indexed by U and U. So if I go back, so if this is a U and this is a U, then you get U dagger U here along the diagonal, and that's the identity. So then now along the diagonal, you just have the trace of the density matrix, which will be 1. So then we can set all of our diagonal elements equal to 1, which is what I wrote here. And we get rid of this unbounded problem. So there would have been different ways to solve this, but this one seems quite neat, and it actually works out quite well for us in terms of the bounds that we can find. And now you get the happy guy. Okay, so now I have like exactly the same slide basically for the contextuality hierarchy as I did for the non-locality one. So level 1, these operators O that you put in front of the row X's are just the unitaries. And then, you go to level 2 and you have 2 unitaries in front and then 3 for the higher levels, and you get this bigger and bigger matrix. And, oh man, I missed this reference. And this is a SDP hierarchy for the contextual set, and this was sort of developed by some project that I was involved in and another project simultaneously. So there are supposed to be 2 references, and now it looks like I've intentionally missed off the other people, but I haven't. I tried, and it's in the references. Okay, so I'm not sure I have time for these things. But you can apply our hierarchy to some games and then find some bounds on them, and the hierarchy does quite well at this, is what I'm saying. And it allows us also to uncover a property that we call monogamy of contextuality, which is basically it's hard to explain this without actually explaining the previous slide that I was going to say. But if you have one party and they make some preparations and then they send it to 2 other parties, the contextuality that you can kind of see between, if the 2 parties that get the preparations sent to them can't signal to each other, the inequalities that they can violate kind of on this arm and on this arm, they are kind of bounded, so you can't maximally violate on both arms at the same time. In some kind of analogy with monogamy of entanglement, you have monogamy of contextuality. So this is in our paper, which I referenced, and we can talk about it more later if you would like. But the thing that I will tell you about is the relationship with Bell scenarios, seen as Bell scenarios have been talked about a lot so far. And maybe you will kind of hear that non-locality is like a sub-case of contextuality, like people will say this sometimes, and I'll try and explain to you like exactly what they mean when they say that. So we've got like, is a Bell scenario a sub-case of a contextuality scenario? So imagine we have a Bell scenario, and now we consider it in the following way. So first, Alice does her measurement and gets some output, and that means that Bob is left with some marginal state of the state that they had in the first place. So we can call this PA given X. So now we view this whole experiment as a prepare and measure experiment on the side of Bob. So a preparation has been made for him by Alice, which gives him the preparation PA given X, and then he does a measurement on that preparation. So now this is like a prepare and measurement on one side, but Alice is like sort of preparing his measurement for him in a kind of steering-y way. And then if we look at the non-signaling constraints in the Bell scenario and see what they mean for these preparations, they actually come out as operational equivalences on the preparations. So what you can see, so here I'm calling this Px is the marginal distribution of probabilities for Alice. And what you want is that the preparation that Bob receives, the average preparation he receives when Alice does the measurement 0 should be the same as the average preparation that he receives when Alice does the measurement 1, so that Alice can't signal to him by doing by the choice of measurement that she makes, she can't signal to him. So the average preparation has to be indistinguishable no matter what her input is. And so the way of writing that is by these preparation equivalences. So this is the average preparation that Bob gets when Alice chooses 0 and then chooses 1 and so on. This should not say 1, this should say n. Helpful. Okay, so now what you've got is a prepare and measure scenario with some operational equivalences on the preparations, right? So now it's a contextuality scenario. But the thing to notice is that the contextuality scenario depends on the marginal probabilities of Alice's side, right? Because the scenario is defined by the equivalences, and the equivalences are defined in terms of Alice's marginals. So so the quantum behaviors in the Bell scenario, you can map those exactly to the quantum behaviors in a family of contextuality scenarios, where like each member of the family is defined by a different marginal distribution for Alice. So like one Bell scenario, family of contextuality scenarios, map. And then to go in the other direction, so if you have a prepare and measure scenario, like a contextuality scenario, and it only has preparation equivalences and no measurement equivalences, and they're of this form. So basically, there are just equivalences, one line of equivalences. There aren't like two lines of equivalences. So you can think of these as decompositions of one preparation into multiple different decompositions that are all equivalent to each other. So in this case, then you can sort of relabel these coefficients in this way and these preparations in this way, such that they look exactly like the non-signaling constraints that we had before. So this is how you map back the other way. So then, so you have the quantum behaviors in this specific kind of contextuality scenarios are now a subset of the quantum behaviors in a given Bell scenario, but with some fixed marginals on Alice's side. So this is this mapping. So then my answer to the question is kind of like, so it's not scenario to scenario, but there is a mapping between the two. So now that we have this relationship, we can ask whether the hierarchies that I've explained to you are equivalent to each other. So we had the NPA hierarchy for non-locality and the contextuality hierarchy. So in the case, so if you're in a contextuality scenario and you only have these preparation equivalences, then yes, you can use NPA to figure out like the maximum violation of a contextuality inequality in the quantum case, or whether your behavior is quantum. But something that we don't know is whether the hierarchies are like entirely equivalent, like level for level. So is level 1 of the NPA same to level 1 of our hierarchy? In every example that we tried so far, you get the same value, but this doesn't mean that they're the same. So this is something that we don't know because of the kind of unitary trick that we're using. So it's something that we'd like to know more about. So if you feel like thinking about this, please do. And then we've got a couple of other things that we don't know. For the NPA hierarchy, we know that this converges if you go in levels as you go to infinity. In general, for the contextuality hierarchy, we don't know if it converges, so this is open. And in the case of both hierarchies, the question of sort of how fast do they converge? So if you have a Bell inequality, like at what level of the hierarchy do you have to go to before you like find the quantum value? I think this isn't super well understood, and it would be helpful for the future. Okay, so I think I'm approximately on time, so I'll leave it there.